Hello, hello. Welcome to another zkForge workshop today. Today we have Stephen Yuan from ZK.
I am going to make Stephen a co-host here. Okay, good. I think you are the co-host, so you should be able to share your screen.
Thanks. Okay, so can you see my screen?
Yes.
Okay, cool. So can we start now?
Yeah, let's go ahead, Stephen. The floor is yours.
Yeah, thank you. Thank you for having me. So I'm the CTO of the ZKM. Yeah, it's so happy to be here to share something about the Ziren. Ziren is a ZKVM from the ZKM. Actually, formerly it's ZK So yeah. So Ziren basically comes from Ziren. We replace the S with Z. Okay. Yeah, today I will introduce I will briefly introduction about what's the zkVM, and then give a brief introduce about the Ziren, and then I will share some use case that can be built on Ziren, and I will also have a prefer introduction about how to build on Ziren. And tomorrow, as my colleague Alice, will have a more specific introduction about how to build on Ziren. Step by step, hand by hand. Okay, so first, I think I assume that most of the audience will be developers and then maybe have some knowledge about ZKP. So here we have introduced about what's a why ZKVM. So I think everyone should be know about the ZKP, right? It's
yes.
maybe most of us may use Zcash and then use some zk rollup. So currently, so maybe 1 or 2 years ago, a lot of projects we're going to build some a new technology that's a zkVM. Basically, zkVM, we may know zkEVM. A zkEVM actually it's I would say solidity that's code-based zkVM. So that means their underlying ISO. ISO means their ISA is the bytes code. And for zkVM, actually we extend it to a more general purpose ISO. So like RISC-V, MIPS, WASM, and maybe some customized ISO like the carrier. So zkVM actually zk knowledge zero knowledge virtual machine. Yeah, it's one kind of the virtual machine that's you utilize the zero knowledge proof to guarantee the integrity and the privacy of the computation. Okay, so it's important is so the main difference is I mean the main difference between zkVM and a traditional virtual machine is it uses zkP to guarantee the integrity. Like for example, if you want to compute something, calculate something on the cloud, but currently we cannot guarantee that the cloud calculates or run your computation according what you have submitted. So you get results, but you cannot verify that the results are really produced from your program. Okay, so if we have the zkVM, so we can make sure that we can achieve the integrity there. So compared with the other zk proof system, zkVM actually has can offer us a high flexibility, because it's a general purpose. You can use a high level language like Rust, GNOME, C++ to implement your sockets, and then you get the proof. Okay, so it's it's get rid of the barrier for I would say the regular developers to implement the sockets. And it's so that's I say it's easy for dev. And the main drawback currently for the zkVM is the performance is not as good as the other proof system, like the application specific sockets or zkEVM, because we have a lot of overhead from the memory checking, from the data serialization or deserialization. Okay. So basically, zkVM works like this. You have some model, compiler like the Rust compiler or the GoLang compiler. They can help us to compile the high-level language program to ERF binary. The ERF maybe can be the RISC-V, WASM, or some other MIPS. So when we have the ERF binary, we begin to execute. We use the executor or emulator to execute the binary, and then we, generally speaking, all the zkVMs will do the continuation. That means we will execute the binary, and then we split the binary into multiple trunks, because if we because it can leverage multiple provers or clusters to speed up the proving. If we just use one machine, the binary would be very large. I would say the binary or the execution sequence would be very large. So it's usually, I would say it's probably cannot use one machine to proving a program for most of the case. Okay, so we employ the continuation, and then we split the execution trace into multiple trunks, and proving all those trunks are in parallel. Then we use the proof aggregation and the proof recursion to generate some to generate the final proof. Sometimes we need to verify those proofs on chain, so we use the stack to snack. That means we can compress the proof to a small proof size and make sure it's efficient to verify on the blockchain. Okay, so basically that. So it's so when we when we see this flow, the main difference from the traditional or the application specific zk sockets is we sometimes use some model compilers or high-level language compilers here, and it's also takes some time to take more time than the zk than the application specific so proof systems. Okay. And so here, after we have some preferred introduction about the zkVM, I think now it's time to introduce the Ziren here. So Ziren actually it's the MIPS is the only one. I would say it's is the first MIPS based zkVM in this industry, and it's totally open sourced. and it's simple, stable. And that also have a very comprehensive developer toolkits, and I will show that in later. And we also have an integral app protocol, which built on Zero to build a universal settlements across different blockchain systems. And so why we choose the MIPS 32? Yeah, I think most of the guys know that Ethereum is moving from the EVM to EVM plus the RISC-V, the dual execution engine. So while we still choose or insist on MIPS, so yeah, and for all the stories, we are incubated by Metis layer 2, and Metis is an optimistic wrap, and we also trying to use Zero to shorter or to optimize the finality time for Metis. Then step by step, we trying to find the advantages that MIPS over the other ISO. We found that for a same program, we can get smaller binaries. That means for same program, like a same roster program, if we use the Zero or zkMIPS, we have a small amount of a relatively small amount of the cycles, than the RISC-V. So you can also check it out on its proof. So what does it mean? It means we can achieve more efficient proving if we have smaller cycles. Yeah, basically, why we have those achievements, because MIPS itself have provided more OP codes or instructions for us to make the sequence short. Okay, so yeah, one special instruction here is ADDU. That's multiply and add, or multiply and subtraction. So this means we can combine two instructions or two instructions into one instruction. This is very helpful for us to shorten the sequence size. And we also have some other special features inside of the MIPS. Okay, so and we also have some data here to show that we are basically we are more instruction efficient here. Okay, so the instruction efficiency means for the same program we have a small number of the cycles of instructions. And for Zero itself, we have for any zkVM, first we need a zk compiler, and then we also need a proof system. So for zk compiler, it's compile the high-level language to ISO. Okay, and then we also execute the binary. The binary, and then we get the witness, and we also need to hand the for zkVM. Actually, it's a virtual machine. That means it have multiple components. Just think about the model CPU. We have different components like the CPU, memory, ALU, and the bus were in charge of the data transfer between different chips. So here we also have a similar architecture. We decompose a program into multiple chips, and for each chips we write the specific constraints and generates the trace table. So okay, so and we also need to we also have concept events, which to make sure the data between the data transfer between the different chips are identical. And we also need to take care of the because for a program or for a trunk we have different instructions, and for each chips so for specific instruction trunk actually we have different instructions, so those instructions may belong to different chips. So that means if each chip we have a trace table, that means all those kind of tables have different heads. So we need to take care of the mixed head trace table commitments. Okay, so in the proof system, basically we need air to express the constraints, and then we also need to commit the memory, because when we run the EVM, that means the EVM is never stopped. So when we put one program inside that to prove it, we need to load the memory first and then run the program, and then after the program ends, we need to serialize, or we need to commit the memory states or memory snapshots. So here we use multi-set hashing to commit or to check the memory consistency when you when you run another program or another not another program, maybe another instance of that program. Okay, so we need to check the memory consistency. And for the cross-chip data, for the data transfer between the different chips, we use the log-up. So yeah, so basically for the multi-set hash, it's from our observation, it's more efficient than the log-up. We actually, before we use a multi-set hash, we use a log-up to do the memory consistency check, because simply in simple words, memory consistency check is just we are using offline memory checking. So basically it's just to check the equivalence of two sets, reading sets and writing sets. Okay, and we are using Planck 3 with Corona field. Corona field is more efficient than the baby bear by like 21%, due to the degree of the S-box in Poseidon 2 is smaller. And yeah, we still have so we still need to build the extension field and elliptic curve on the big bear, on the Corona bear for the multi-set hashing. Okay, so yeah, I just mentioned this concepts. So for more detail, I think yeah, we can talk offline or check out our website, our document site. And then we have some industry leading performance on the GPU right now. And for proving speed, our single RTX 4090, we can achieve like 2.06 million hertz. The hertz means how many cycles per second. Yeah. Okay. So it's and our GPU we provide also currently our open source code is yeah, we just open source our CPU approval right now. For the GPU approval, you can only access it our proof network, but yeah, so it's deployed on the cloud, and we can on single like RTX 4090 we can achieve 30 times yes faster than the CPU approval. And in the future we will also will open source our GPU approval, maybe maybe in the Q1 2026. And okay, so we are the second zkVM listed on isProof. isProof is a layer 2 bits alike projects backed by Ethereum Foundation. And we have a basic summary from the isProof. Okay, so yeah, so I think most of that has been introduced in the previous slides. Okay, and yeah, here is our developer tool chains. So first we support multiple languages: Rust, C++, Go, and we also support any static language. That means if you can compare your language into a static library, so we can support. We can use FFI to Rust FFI to load it and prove it. So basically, for any static languages, we can support it. Of course, you need to the language need to support the static binary compilation. And for our toolchain, we have our self-maintained toolchain, include the LLVM, clone, and the CC. So it's basically platform independence. Yeah. So okay. So for our SDK, we have a built-in SDK in Ziren. So it's it's provided local approval and network approval. For the local approval, that means you can approve on your computer, and then you can you can prove on your local computer, gets proof and verify it anywhere. And for the network approval, it's GPU powered. We have a SaaS API. That means we have a RPC API that you can use the RPC to submit your program, your inputs, and then you will get the outputs. You will get the outputs and the proof. Basically, the outputs would be the public input. And we have a ZKM project over the SDK, which is a framework allowing you to write your guest program very easy. So yeah, we also provide a CLI. Let's go to the CLI introduction. Okay, so it should be here. Okay, for CLI, it's a single command line. You can use the after you install the CLI, and you can use the Ziren new to initialize projects. Then inside the project, the layouts would be like this. You have the contracts. Yeah, we only support the being 254. So if you have some other, that means of course it's for the EVM or EVM compatible blockchains. If you are Cardano or some other Cardano Tone or some other projects, maybe you need some other. I would say we don't support right now, but we have plan to support the different blockchain for the BRS 12381 based blockchains. So we also have a guest program here and a host program and a host directory. So for the host, it means for the guest, it means the program you want to prove, and for the host, it's we compile the guest into the MIPS binary, and then we invoke the proof function to generate the proof, and then you can do anything because it's host. It's like a normal zk virtual machine. You have the guest program, you have the host. So in the host, so at the host side, you can do anything to interact with the external worlds, like you by the by the HTTP or HTTPS. But inside the guest, it's no SSD based. That means you cannot access the file system. You cannot access the internet. You cannot access the kernel by creating a new thread or process. Okay, so yeah, so the layout will be like this, and we also have a contract here. Like I mentioned, we can produce a solid web file, so it's simplify your on-chain verification. And then and then you can use I think it's better to have more specific examples here. We have a lot of examples under these projects, and for example, we take a look at the Fibonacci. Maybe Fibonacci. Okay. So we have a guest problem here. It's a single. It's a single crate, or it's a single raster project, and you need to use some macro. You need some clear. You need to use node STD and node make here, and then you claim the entry points. Then you can read the input and read the data from the inputs from the host side by this function, and then you can commit the public inputs. That means you can need to declare here the n is the public inputs. Then you implement your circuits. Okay, and at the host set, we need to first we need to write a build file. Inside this inside the build.rs, we need to compile the guest explicitly, and then after we compile, we actually have the binary, MIPS binary, and then we begin to load the binary. Like we need to include the binary here, and then we do a setup. Okay, it's a stack setup. It's a stack proof setup. Okay, so that means we commit the constants polynomials first, and then we prove it with the clients. And okay, so for the clients, actually it's initialized here. So for the it's a local. So basically, it's a local prover. So if you want to use the network prover, there is a different initialization here, and then we read the inputs and public inputs. Okay, and we also need to purge the okay. Here we also have to initialize std_in. That means we write the inputs into the guest program, and then we when we proving the program, after we execute the program, we proving it, we get the public values. The public values actually comes from the commit function inside the guest program. So after we proving the program, we can still do more operation here. For example, if we want to generate a compressed proof, a gross 16 proof, or plank proof, we can do like this. We can do more. We can set up the final proof format to gross 16, so we can generate the proof here. So basically, if you guys are familiar with the SP1, our API is very, very similar to SP1. So I think it can easy developers to use our SDK and toolchain. So okay, and for more examples here, if you want to build some production ready or production zk applications, you probably need to use the aggregation. That means we need to we like we mentioned, we use the continuation, and we split the different the entire program execution into multiple trunks, and then we prove different trunks in parallel, and then we get say trunk proof. We get the proof. We put the proof inside this program. That means you have multiple trunk proof, right? Then you write the program, you digest those proofs, and then you verify those proofs and file. And this program will generate another proof. So that proof was the aggregation proof for your trunks proof. Also, basically, this is a very actually there are two different approaches to do the proof aggregation. This is we say it's based on the aggregation guest. You can see that it's very simple. You just read the proof from the host side, and then you run the verifier. Actually, the verifier is a pre-compile. Run the you verify the proof. So finally, we have a proof for this program. So that proof will be the aggregated proof. And another solution is so when we use this program, which means we need to use the compiler to compile this program into MIPS, and then we prove the MIPS sequences. And if another approach is use the application specific sockets, that means we use the AIR to implement there's verification logic. So for the application specific aggregation sockets, it would be more efficient, but it's not. I would say the scenario for this approach is limited, because we cannot because if we use the guest, it's more flexible. You can implement any logic here by yourself, but if you use that the application specific aggregation sockets, probably it's not easy to add something new or change something there. Okay, so yeah, that means I want to say we have a lot of examples here. We also support the Bitcoin. We have a Bitcoin example. We also have EVM example. Okay, for the EVM example, it's not here. It's in another repo. Maybe I think it's really simple to find it out. Or if you cannot find it, you can ask us. Okay, and we also have some customers example. Yeah, we also have some. Okay, for the Tendermint, we also support the Tendermint. Yeah, here. So it's a customers, Rust customers SDK. So okay, so that's basically how we have a lot of support for the developers, and for all the things you want to know, maybe you can find more details in our websites. Okay, so for the use case, the first use case I will introduce the zkRAP. Actually, it's the most widely used use case, I would say, because you can check that for not only the EVM ecosystem, Ethereum ecosystem, the Bitcoin, but also the Bitcoin ecosystem. Maybe you can check out maybe there are more than 100 Bitcoin zkRAPs today. So for the zkRAP, actually, it's often asked to extend the layer 1 with the programmability and the high throughput. Okay, so for the EVM Ethereum ecosystem, yeah, of course, it's proving the scalability for the Ethereum. For the Bitcoin, actually, it's proving the programmability to the Bitcoin itself. Okay, so so here is the use case we are we are collaborating very closely. That's Go Network. Go Network basically it's Bitcoin zkRAP. And it's very hard usually to verify the proof on Bitcoin by the Bitcoin scripts because the scripts functionality are very limited. So here actually we are not verify the proof directly on the Bitcoin. We actually leverage the BitVM2 protocol. It's an optimistic computation with it's a optimistic computation by scripts. That means we commit the execution. First, when we have an off-chain program, we execute the approval, execute it, and then commits the results of the execution of Bitcoin. And then if someone have some disagreements or found some fraud in that execution, he would submit a challenge transaction. If a challenge transaction is submitted, the approver need to review the execution trace, and then after the approver will review this execution trace by a taproot. If then the challenge begin to find the fraud points or fraud proof from this execution trace. If the challengers can find it, he can disprove the prover, and then stop the prover to claim some assets withdrawal or something like that. Okay, so basically it's commit challenge game. Okay, so by leveraging this protocol, we the Bitcoin zkRAP use the BitVM2 to run the word file of the zkVM. So this can make sure that for any off-chain computation, we can prove it by zkVM, and then we can use the BitVM to verify the proof on Bitcoin. Okay, basically that's how it works for most of the BitVM based or for most of the Bitcoin zkRAP. And for the zkVM itself, it can be used by multiple components in the Bitcoin zkRAP. The first one is like you generate proof for your off-chain computation, and another place is you can use it in the BitVM itself. Okay, so for BitVM itself, when you generate the scripts, Bitcoin scripts for the proof file, actually the proof, the script size is very large. Actually, at the beginning, the script size is about 7 gigabytes, but after 2 years of optimizations, the size is is less than 1 gigabytes right now, but it's still too large. So another technology is the gap socket. The gap socket basically can reduce the script size to less than 100 kilobytes. Okay, so for the gap sockets, actually we can use the zkVM to prove the correctness of the yes, we can use the zkVM to prove the correctness of the gap sockets construction. Okay, so yeah, and this is for the zk for the Bitcoin. Yeah, we have a, yeah, I present the BitVM Bitcoin layer 2 because it's really there are a lot of research and developments on this technology right now. And another widely discussed or widely used use case is the sign data. We can see that PSE actually have a lot of research or developments over those over this field. The zk email prove the specific facts about email contents, the zk identity, like the annual era from India, and to prove the natural identity of the people. And we also have some use case, have some applications, production ready applications, electronic passports. And for the zk contents, I think zkTLS is very is discussed a lot. It discussed a lot. Yeah, there are also a lot of projects that focus on the zkTLS, like the zkPass. Yeah, and for zkPDF, actually, it's a very new concept, right? Yeah, it came out. It came out. Yeah, 2 or 3 months ago. By the PSE. It can prove the effects from the digital standard PDF without reviewing the full documents. PDF actually it's a very popular data formats, and if we want to and it's easy to distribute it, right? Because it's immutable. But if we want to hide something or prove something of prove some data of inside of that documents, but we cannot avoid we still can modify by some model tools, right? If we have the zk proof to proving the data, and then you can verify the authenticity of the data by zk proof, so it can be more secure for you to sign some documents or maybe contracts based on the zk PDF. And another is GameFi. First, very interesting use case is the off-chain logic verification. So most of the game actually happen on off-chain. So if we want to really build on-chain applications, okay, zkVM is a very suitable technology for that, and it can also help you to add your moves or strategies. So for example, if you want to play some like the cards game, maybe you want to generate some random number, but if you use on-chain random generators, maybe it's not private. It's easy for the other players to get your randoms. So with the zkP, it can help you hide that and make the games really fair. And we also can use it to header the game status or do some of the cross-chain progression here. Yeah, I think as far as I know, GameFi, there are a lot of zk-based GameFi right now. Yeah, and then the final use case, at least here, is the DeFi. So use with the D factory, it can help us to hide or to build more interesting, the DeFi assets or DeFi protocols. Yeah, so like the synthetic assets, we can use the zkVM, zkP to build some, private synthetic assets, and we also can help the people to hide or build to hide your assets on chain, and then make it more comfortable for the lender or the borrower to do the to participate in the lending or collateral protocols. Now we also can do the anonymous voting system and build some private order book on the chain. Okay, so for this kind of, I think there's still a lot of other applications like the zkML, but for zkML, I believe it's still have a long way to go because everyone is focusing on the LLM, and for the LLM, if you want to use the zkML or zkLM to proving the to achieve the verifiable AI or verifiable agents, it would be very, very inefficient. And if you want to add, or if you want to employ the zkP in the training progress in the AI in the AIM model training, it would be very, very slowly and even not practical right now. So basically for the zkML, I think there's some team that focus on this, especially focus on the verifiable agents. But I would say, zkVM may be not the best infrastructure for that. Okay, so as for the vision, we want to build the unified liquidity for across all the blockchain, because zkVM actually can prove in all the smart contract system of different blockchain systems of the different blockchains. So basically, we can use the zkVM to prove in different layer one thing. If we want to verify that one transaction happening in one blockchain, we can generate a proof for that transaction, and then we get that proof and verify this proof on another in another blockchain. So that means actually there's no bridge. We sometimes call it bridgeless bridge. So we can verify any events from any blockchains. Yeah. Okay, so basically that's all for my presentation, and we have a lot of details. You can check it from our websites. Yeah. Okay, so yeah, for the left, I'm not sure if there are any questions about my.
Thank you, Stephen. This is also a workshop about Ziren, about the zkM. We as ZK Monkers are very surprised about the project, and we have a lot of ideas to how to implement that. Well, amigos, amigas, ZK Monks, if you have questions, you can ask now.
Yeah. Basically, this is my second time to introduce the zkM, zkMIPS in zkMonk.
Great. Go ahead, buddy, with your question.
Can I go? Okay. Hello, everyone.
Hello.
My question goes like, what's the recent use of zk zkM in the industry. Like, what possible problem are guys are you to solve? Like, any real world problem?
Sorry, it's not very clear. Can you please
Okay,
repeat?
I just want to know, like, I want to know the recent solution that zkM have been used to implement, like, have been implemented to solve real world problem, like it's of recent.
Oh, sorry. I'm really sorry. I cannot hear it very clear. Uh,
Maybe you can write in the chat, please, because we can hear you clear.
yeah.
Okay,
Let,
I will.
let's go, Cryptosaurus. What is your question?
Yeah, so I have this question where it's a bit technical, where this, if you can put some light on the beginning of how MIP S32 and how is it related to RISC-V, because this kind of is very interesting and I would like to know more about it. So.
okay, so you mean so your question is how to verify the proof on Bitcoin, right?
Not on the Bitcoin, just on the basics of MIP S32, and how, like, you had in the one of the slide in the starting slides you had, right, related to risk V32. Yeah, the second slide, if I am not wrong. Second or third.
Third one, right? This one, right?
Next one, next.
Okay, yeah.
Yeah, this one.
Okay. So yeah, basically, for the MIPS 32, actually, it's we have about six. We have the MIPS 32 has six release. So the total instructions or OP codes of MIPS 32 is more than 76, is more than 76. And I think, of course, for the RISC-V, for the RISC-V, I mean RISC-V 32 two different extensions, because the RISC-V is modular design. It's of modular design, so that means you can use different extensions to extend the RISC-32 itself. So I would say first, MIPS MIPS 32 is more simple or more consistent. That means we only have one. We even though we have 6 release, but for all those 6 release, they are compatible with each other, or I would say they're forward compatible. So if you use like the MIPS 32 or release 6, it can be compatible with the previous release. So that means if no matter which release or you use, it still can be well handled by its competitor or its emulator. Because the emulator is in charge of the execution of the binary. Okay, so for the RISC-32, basically you need to take care of the compatibility issues between different extensions. Maybe if you compiled based on some extensions, then you run it in another platform or another emulator, maybe it's not be well executed. Okay, so B specifically, MIPS, we have more registers, like we have low or high registers for some OP codes, like the add multiple subtraction. Basically, it's it's compared to instructions into one instruction. Like we actually, if for multi-add, we do them, we have three inputs. We have three inputs or operands, and then you multi A and B, and then you add C. Okay, so this actually specific officer OP codes from the MIPS 32. If you want to implement it on RISC 532, you need to maybe implement your own OP code by the Cisco. Of course, we know both the ISO provided the Cisco. Okay, so the Cisco base is very specific or very customized instruction. And we also support relatively larger memory. The MIPS supports about 4 gigabytes memory space, and RISC-V support 256 megabytes. So we also have a very non-jump or addressing instructions. Yeah. So we and we also have more conditional selection instruction like move by 0 or not 0. So basically it's a very so all those instructions actually are provided by MIPS 32 itself. We don't have to consider the compatibility issues between like different release or different extensions. Actually, there are no extensions in MIPS 32 except the Cisco. Okay, so yeah, so this actually for the you can tell that RISC-V based zkVM, they only about 40, maybe 46 or 48 instructions. Yeah, and I would say most of all of the zkVMs just supports the I and M extensions, no other more extension, because it's not very practical to support that in zkVM case. Yeah, I'm not sure if I answer your question exactly. Yeah, maybe if you have more questions, we can discuss. Yeah, offline you can send me.
Yeah, just for that, where can I connect? Is it Telegram or Twitter? Because I would like to learn more about it.
Yeah, of course. I will share it to you later in the chat box.
Okay, thank you.
Don't forget, we can continue the conversations in our Discord too.
Okay.
Steven,
Yeah.
We have one more question in the chat. They say,
okay.
I was asking for the best use cases of zkM when it comes to real world problems.
Chemistry, the best use case would be the good network. Yeah, the good network. Good network is the Bitcoin native. So actually, I would mention the strategy of zkM. We are not only built. We are quite different from the zkVMs like the SPU and RISC-0. Actually, they are built a proof network and just build a proof network. But for us, we are doing something more than that. We also care about the verification layer. So for Bitcoin, we are not only provide the zkVM for good network, we also help it to build the verification layer. That means we also build, integrate zkVM Ziren with the BitVM itself. I think we will have another announcement later this month, maybe in token 2049. We will have an end-to-end demo that show how to use the Ziren BitVM GC to demonstrates how to verify the proof on Bitcoin. Yeah, actually, this is the optimized version of BitVM2. The Go network already have a testnet of the BitVM2 right now, but as I mentioned, it's still very expensive to if there is a challenge there, and the prover need to commit the execution trace, and the execution trace over the Bitcoin script maybe as large as 1 gigabytes. Yeah, it's a 0.9 gigabytes, but yeah. So, but based on the gap sockets, BitVM2, it's about 67 kilobytes. Yeah, that means that's around 1,000 times cheaper. Yeah. Okay, so yeah, we will. Yeah, so for that use case, I think we have a lot of details in we have some details in our website, and there are a lot of details on Go network. You can search the Go network on Twitter. Search on ZK is there where I can get some formal material guess with the crew. Yeah, of course. The first way is use the ZK Monk's Discord, right? I think I'm in the Discord. Yeah. So if you can ask there, and tag me there, so I can answer any question if you have, and yeah.
Yeah, sure.
And of course,
and also we have the other mentors in our Discord too. So it is important to share the questions there, because all can learn in that way too.
Yeah.
Yes. Well, Steven, we have a very great time with you. Thank you for sharing your knowledge and your time with us.
Yeah.
People, tomorrow we will have another great session with Alice.
Yeah.
So see you tomorrow the same time, and continue the conversation in our Discord.
Okay, thank you, guys. Thank you.
Thank you. See you tomorrow. Bye bye,
yeah,
guys.
bye.